Irrigation engineering is the design of regional economic lifelines. If mathematical tolerances are wrong, crops die from drought, or entire landscapes are ruined by flooding. This flowchart breaks down the highest level of irrigation systems. We divide the entire field into two classes: flow irrigation, where water moves naturally by gravity, and lift irrigation, where it must be pumped mechanically. Zooming in on this secondary diagram for flow irrigation methods, we see a structural split between uncontrolled wild flooding and the much more precise controlled flooding techniques. In these layout diagrams, we contrast two approaches. Top, the zigzag method forces water through a winding path of square check plots. Below, the furrow method routes water into narrow, targeted ditches between rows to minimize evaporation. Choosing how water travels across the surface is an important initial step, but the primary engineering challenge begins the moment that water penetrates the ground. As water infiltrates the surface, it splits into two paths. Some is captured near the roots for plant evapotranspiration, while the rest escapes downward as deep percolation. Managing this invisible cycle is the core metric of success. This diagram maps the classes of soil water. Think of soil as a rigid sponge. At its absolute maximum, all pore spaces are filled, reaching what we call saturation capacity. Notice the top zone marked gravitational water. This is superfluous water that gravity immediately pulls downward. Once that excess drains away, the soil settles at its field capacity. This is the moisture retained by capillary action against the pull of gravity, and it represents the maximum usable reservoir for the plants. However, the crops cannot access all of it. At the permanent wilting point, the soil holds the remaining moisture so tightly that root systems can no longer extract it, leaving only unavailable hygroscopic water. To calculate the actual physical depth of water available to the crops, we use equation 3.2a. We take the dry unit weight of the soil over the unit weight of water, multiply it by the root zone depth, and then multiply that by the percentage difference between the field capacity and the wilting coefficient. That calculation gives you a strict physical depth in millimeters. Your entire water supply budget for a growing season must be precisely calibrated to fit inside that narrow margin. To figure out exactly how much water to release from a dam to fill that specific soil margin, we have to build a chain of requirements, calculating backward from the plant's consumption to the river. This text details the first link in that chain. Equation 3.28 shows the consumptive irrigation requirement, or CIR. It's the baseline amount of water the crop needs to survive, minus any effective rainfall the area already receives. Moving down to equation 3.29, we establish the net irrigation requirement, or NIR. Here, we take the CIR and add the extra volume of water needed to actively leach harmful salts out of the root zone. Next is the field irrigation requirement, shown in equation 3.30. Because applying water to a plot isn't perfectly efficient, we divide the NIR by the water application efficiency to account for local surface runoff and deep percolation. Finally, equation 3.31 gives us the gross irrigation requirement. We divide the FIR by the conveyance efficiency to account for all the seepage and evaporation losses that happen as the water travels through miles of main canals. Let's test this logic. If a field requires 146.6 millimeters of water, and the canal network delivering it operates at an 80% conveyance efficiency, what is your gross irrigation requirement? You have 3 seconds. The answer is 183.25 millimeters. You divide by the 80% efficiency factor. You do not multiply. You must source more water at the dam than the field actually needs, because 20% of it will be lost in transit. If you fail to scale up your dam release calculations using these exact efficiency factors, the water you send will vanish into the soil long before it reaches the roots. On the flip side, oversupplying that gross irrigation requirement without establishing adequate drainage is equally destructive. The water table rises, choking oxygen from the plant roots and depositing heavy white salt crusts across the surface. Physically, this waterlogging is an inversion of the soil sponge. The local saturation capacity overflows upward, with the groundwater rising directly into the root zone. To counter this, engineers install subsurface tile drains. These perforated pipes sit below the root zone to capture the excess deep percolation and artificially drain it away, lowering the water table back to a safe depth. To recap the system, Moisture in the soil exists on a strict timeline. It drains rapidly from total saturation, stabilizes at field capacity, and eventually dries out to the lethal permanent wilting point. And to hit that target field capacity without overfilling the system, we use this master chain equation. We build up from the plant's consumptive use, add leaching needs, and systematically divide by our system efficiencies to find our exact gross irrigation requirement. Designing these lifelines requires perfectly balancing the mathematics of supply with the physical realities of soil drainage. Get it right, and a barren region thrives. Get it wrong, and you drown the very crops you're trying to save.